prior to the point at which they could make these measurements, they were asking the questions of themselves, starting with a guy named Helmholtz, is what is the structure of the interface? And it was clear from earliest times that there was a the capacitive type of interfacial structure. They understood that there was some sort of a capacitor type structure at the interface. And so Helmholtz came up with a model of the interface that was able to capture the idea of a capacitive element at the interface. And so Helmholtz said that, and we've already heard Helmholtz as being the inner and outer Helmholtz layers. He said ions lined up like little soldiers right on the line, a certain distance away from the electrode interface. And so he said the distance was approximately 10 angstroms away from the interface, and all the things that we're going to absorb to the electrode were right on that line. And probably for ease of mathematical computation. And when you do that, you can actually calculate the physical behavior of that type of interface. First of all, he said, well, that kind of thing would be a charge-separated material, and so it acts like a capacitor. And if you put the terms in like a capacitor would be, a parallel plate capacitor, you get an equation like this. Where V is the voltage across the capacitor, 4 and pi are geometric factors, D is the distance here, sigma m is the specific charge on the surface, or the charge density, so how much charge per unit area, and epsilon, capital epsilon, or epsilon is the dielectric constant of the medium, so the dielectric constant of the capacitor. He said if you take the derivative of the voltage, you get this. Now this unfortunate kind of notation here, we have distance, and then we're going to take the derivative of the metal charge. And if you take the surface tension, which is essentially the change in the metal charge as a potential is changed, again holding everything else constant, you get equal to minus 4 pi d over epsilon if you integrate that and evaluate your constants, you get that lambda is equal to lambda max minus 4 pi d sigma m squared over 2 epsilon, I think that's what it is, yeah. Or since sigma m squared is equal to v squared sigma squared over 4 pi d squared, you can substitute that in, and okay, in other words, the surface tension is a constant called lambda max, and a term that's got the dielectric constant in it, and then a term that's the proportional to the square of the voltage applied to it. Well, that's a parabola, equation for a parabola. So if you plot that, you see this. And so Helmholtz came up with a model based on a capacitive type model, and he said, well, the PZC is here, and that gives you lambda max like you want, and so on. So essentially he made the relationship between the surface tension and the capacitance of the electrode. And by analyzing the data that you often see, you could come up with the fact that the distance is approximately 6 angstroms, and the dielectric constant of the interfacial region was about 7. Now, if you look in the CRC handbook and look up the dielectric constant for pure water, it's not 7, it's about 78. So one of the things that this sort of treatment already showed them was that the dielectric constant of the interface is not the same as the bulk solution. And why is that? Well, it turns out the dielectric constant is influenced by the ordering of the dipoles in the interface. And so because water is ordered as an ordered dipole structure right at the interface, the dielectric constant drops and it becomes less able to hold charges. And so using the Helmholtz model, they developed that the capacitance should be about 10 microfarads per square centimeter, which is pretty close to the mercury situation, about 20 microfarads per square centimeter. Well, the Helmholtz model assumed that the capacity of the dielectric double layer was constant, and that the shape of the surface tension versus potential was a perfect parabola. Now, in many cases, that's roughly true, but it's not true enough to really be satisfactory. The shape is not parabolic in many, many cases, not even close to parabolic. And the capacitance is not constant. You can actually measure the capacitance at very different potentials, and you see it's not a constant. So Helmholtz assumed the constant capacity. So what kind of things can we include in our model to help understand the variability of the capacitance and the non-parabolic shape of the surface tension versus potential? Well, another theory that was developed was the so-called Gouy-Chapman theory, named after a guys named Gouy and Chapman. And it's about 1910, so this is not too recent sort of things. But they made an important contribution in that they suggested, you know, Helmholtz may or may not have been thinking about this correctly, but for sure, the ions that are at the electrode surface are not going to be stuck in a line at the electrode interface. They're not going to be just sitting there. They realize that the ions will be randomly distributed, not randomly distributed, but will have a distribution that's a Boltzmann distribution. So they included a Poisson-Boltzmann distribution of ions in the system. And so the ions were not necessarily at the interface, but they could be randomly distributed about the interface, and that would depend on temperature and so on. And they made the important assumption that ions were point charges. And what they found out is that after they did that, we're not going to really go through their derivation. It's a little messy. But they got a distribution of capacitance that was not a parabolic distribution. Remember, Helmholtz assumed a constant capacitance. So this is an important result because now the capacitance is no longer a constant. So that's more reflecting of reality and what people are actually seeing. And what this is actually a hyperbolic sine. So this is a sine H type curve for the capacitance. It turns out that in very dilute solutions, this is roughly what people were seeing in the capacitance, right near the PZC. That would be the minimum. They actually saw a dip in the capacitance that had this hyperbolic sign dependence. And so for dilute solutions, 10 to the minus 3 molar and less, you see very reasonable agreement with this particular feature of the thing. However, Gouy-Chapman theory started to fail dramatically as they went to higher and higher concentration. So what you saw was that the capacitance was always this hyperbolic sign, but it just kept increasing and increasing and increasing as we increased the concentration of ions in solution. In other words, all you needed to do to make this really tremendous capacitor was to make the concentration very large, and you'd get 1,000-fold more capacitance than you would at a lower concentration. And that's not true. People realized that quite right away, that that was not reflective of physical reality. But as I said, certain experiments, in particular experiments of a material called sodium fluoride, saw curves that were somewhat interesting, and they would see curves like this, where we had, say, 10 to the minus 3 molar at the bottom, 1 molar at the top. And you see right at the PZC, yeah, it looks kind of like what Gouy Chapman predicts. Well, the main problem with Gouy Chapman is you can't really assume that the ions are point charges and then allow the concentration to become large, because you can no longer assume that the ions are going to be separated by any reasonable distance. They have to be separated by some distance because they're physically not, they're not point charges, they have a radius. And so a guy named Stern took Gouy Chapman theory and modified it to include the idea that ions are not point charges. This is about 1924. And now, instead of, not only will you have the Boltzmann distribution of the charges, but they also have a physical radius. So as we increase the concentration, you can think in qualitative terms that you just can't make the capacitance larger and larger because there's no room for those new molecules to get in there. Whereas in the Gouy Chapman idea, we've got ions and molecules, they could pack in as tightly as they like because they have no size, and so all these can be very close to the electrode surface, and that's why the capacitance kept getting bigger and bigger and bigger. Stern said, no, you can't have these an infinite number of molecules or ions at the interface. They have size, so that ultimately limits how much can be at the interface. And so that really helped the theory quite a bit. And so what Gouy Chapman Stern theory now suggests is the following. The capacitance of the double layer is now something like this, where there is a certain fraction of molecules at the interface, and those certain fraction of molecules at the interface are basically going to be there no matter what. Okay, as long as we've got a certain number of ions, because they're going to be absorbed, and they can only get so close. So there's always going to be this sort of layers. You can think of the people lining up at the at a construction site on the fence. You know, if there's a number of people there, all the spaces are going to be full right at the fence, but you know, then people are going to be away from the fence. And so as long as there's some people there, there's going to be a line right at the fence, and then there may be any excess will be away from the fence. And so there's going to be some around the interface, and some will be right at the interface. So Gouy Chapman Stern says that there's going to be two capacitances. One is the Helmholtz capacitance, and one is this C sub D, which stands for diffuse capacitance. The Helmholtz capacitance arises from the separation of charge that arises from the ions that are non-specifically absorbed right at the interface. And that's going to be fixed. And effectively, it's going to be concentration independent. Because pretty much for any amount of concentration, as long as there's some ions in there, they're going to be on that line. On the other hand, the amount of materials that are diffused not at the line are going to be dependent on, they're going to be some distance away from the interface, and how close they are to the interface depends on how concentrated they are and the Boltzmann distribution of them. And so this diffuse layer is concentration dependent. The diffuse layer capacitance is concentration dependent. Whenever we have two capacitors in series, that acts just like you might have learned in physics a long time ago. The total capacitance, or C total, It's going to be the reciprocal of the total capacitance could be the reciprocal sum of the Helmholtz capacitance and the diffuse capacitance. Now, when the diffuse capacitance becomes large, which happens at high concentrations, this term essentially drops out. And that means that the Helmholtz capacitance is the only thing that you see at high concentrations. So this means that at low concentrations, you get the nice Gouy Chapman type dip in the capacitance, because at low concentrations the diffuse part of the is going to take over, because now it becomes sufficiently small that we can think about that. The Helmholtz layer becomes negligible at some point. And then as the concentration increases, though, we start to see less capacitance, and eventually becomes flat, because at high enough concentrations there is no effect on the diffuse layer. And so this is now not exactly the same, but much more similar to what people are actually observing in the experimental results. Now, what's that mean for experimentalists? Well, it turns out that it has some pretty important implications for doing electrochemistry now that we have a pretty good model of the distribution of charges near the electrode surface. What that suggests to us is that as we go from the interface, again this is going to be x away from the surface, as we go from the interface to the outer Helmholtz plane and out into solution, we're going to start to see different sorts of potential changes. Remember what I said is that this adsorbed layer of ions on the surface is going to cause a potential drop. Well, so will this adsorbed layer of ions that are diffusely milling about near the electrode surface but not right at the plane. So what you're going to see, if we look at the potential, we can specify that there's two start and stop points. One's the metal potential and one's the solution potential. There's going to be a sort of a linear drop in potential to the outer Helmholtz plane. That takes care of the fact that there's material is absorbed there. And then there's going to be this more gradual change in the potential as we go out into this diffuse region, because those molecules are not all in one bunch, they're diffusely separated from the surface. So there's this sort of exponential change in the potential. This point here is the potential at the outer Helmholtz plane. It's called phi 2. Phi 2 refers to the fact that it's the outer or the second plane of the electrode surface, and so it's a phi 2, what they call a phi 2, and you'll see later a phi 2 effect on that. Now it turns out that the more dilute solution that we've got, the more this effect of this diffuse layer starts coming into play. So if we go to quite dilute solutions, what we see is that this term phi 2 is now much closer to phi metal, in other words, the metal potential. So this, what they call diffuse layer, is important at low concentrations. In other words, millimolar concentrations of electrolytes and so on. What does that mean for us practically? Well, as we go to very low concentrations, that means that the potential that we see when a molecule arrives at the outer Helmholtz plane is less than it would see than if the molecule would arrive at the outer Helmholtz plane under more concentrated solutions. Now I'm going to stop here because we're out of tape, and we'll take a break, and we'll continue in a minute.